In the last section, we took a look at double integrals over rectangular regions. Those are easy. There are constants on both ends. They made a nice rectangle in the base. But the reality is most of the time when you do double integrals, you're not going to be integrating over rectangles in the base. There's going to be something else there. Irregular regions, two functions that intersect at a point that form the base of an object, even the triangle or something that could form the base of the region that you're integrating. So these are double integrals over general regions. This is, again, the PowerPoint, the full PowerPoint that's up on the website has all the different pictures and the explanations. But we're talking about looking at maybe this region R here as the base of the solid that then forms above it. How do you find the double integral? Well, you've got to figure out where your x's go and where your y's go. So when you integrate, in this case, the y's, right? Here's my little picture here. The y's are going to go where? They're going to go from g of x to h of x. G of x is this function on the bottom here. H of x is this function on the top here. So that's where your y's are going, right? This is your y-axis. Looks a little bit different. That's the way your y's are going, from h of x to g of x. Your x's, on the other hand, are going where? They're going left and right. So they're going from a to b. So your x's are going from a to b. Your y's are going from g of x to h of x. And once you set those bounds in there, then it's just a matter of integrating. So first figure out what your base looks like, then figure out what the limits of integration are in terms of which way your x's and y's go. So this just says sketch the region and set up the integral. We don't have any integrand yet. We just have to figure out what this looks like. So this says the region are the x's and y's. That little dots means such that the x's go from 0 to 2, and the y's go from 3x squared to negative 6x plus 4. Ooh. Let's make ourselves a little graph here. 3x squared is an upward-facing parabola. Probably not as wide as I made it, but it is. There you go. All right. Negative 6x plus 24 has a y-intercept of 24, which, look, I measured it out. It's exactly there. Haha. And it comes down like this. So this at least gives me an idea of what it looks like. And it says the x values go from 0 to 2. Now, what does that look like? Well, that means that the x's are going to go from 0 to 2. And the y's are going to go from the top to the bottom. So this 6x plus 24 is the top of the region. That 3x squared is the bottom of the region. So that's what the base of the region looks like, right? It stops here at 0. It doesn't go past that. And we didn't actually calculate the intersection point, so I don't know if it actually goes all the way to the intersection point or not. But I do know that the 3x squared is on the bottom. The 24 minus 6x is up at the top. Now, the 3x squared being on the bottom and the negative 6x plus 24 on the top, those are measures of y. How about the x's? The x's go from 0 to 2. So 0 to 2 is an integral with respect to x. And we don't know what the function is, so let's just call it f of xy. That's the surface that's sitting up on the top for which I'm trying to find the volume. So that's how I set it up. If you look at the y's are in green. Bottom one is 3x squared. Top one is a line, so it goes from the curve to the line. The x's go from 0 to 2. Great. Now what? Now how about we try a couple of problems that have those. So this says evaluate the integrals. This time they're already given to us. So the y values range from x squared to x plus 6. So I said first integrate with respect to y, evaluate, simplify, and then integrate with respect to x. All right, simplifying as you go along will be a big help because not only will it save you time, but you tend to make mistakes while you're integrating if you have these massive integrals. If you can simplify them even a little bit, that helps out. So let's solve this. The outside integral was 0 to 3. The inside integral was x squared to x plus 6. And the integrand was x minus 1 dy dx. So let's integrate first with respect to y. All right, so this piece here, integrate with respect to y. If I take the antiderivative of x minus 1, the antiderivative of x with respect to y is just xy. minus y. Evaluated where? Evaluated at y equals x plus 6, and evaluated at y equals x squared. Interesting. So now I replace the y with those things. Maybe it would help if I factored out a y, made it y times x minus 1, and now I don't have to do the substitution once. So I can replace this y over here with an x plus 6, and then with an x squared. So I get x plus 6 times x minus 1 minus x squared times x minus 1. All right. Yeah, I could factor out an x minus 1, but I don't know if that's going to help me all that much. I'll get an x squared minus x plus 6x gives me plus 5x minus 6 minus x to the third plus x squared. So what simplifies? I end up with a negative x to the third plus 2x squared and then plus 5x minus 6. Now comes the easy part. This gets integrated with respect to x from 0 to 3. All right, so there might be fractions in this. Antiderivative of negative x to the third will give me negative x to the fourth over 4 plus 2x to the third over 3 plus 5x squared over 2 minus 6x. Good news is, evaluating at 0 gives you nothing. Bad news is you got to evaluate all this at 3. So this gives me a negative 81 over 4 plus 2 times 27 over 3. Oh, that's hopeful. Plus 5 times 9 is 45 minus 18. All right, if you combine this, let's see, 27 over 3 is just 9. Oh, look at that. This over here is 18. This over here is negative 18. So they go away, and I'm left with negative 81 over 4 plus, let's call that second fraction 90 over 4. 90 minus 81, 4, gives me 9 over 4. Done. Okay. So that's my answer. I integrate it first with respect to y, then with respect to x. All right, let's take a look at another one. This says I want to evaluate this integral of x plus y. Again, that dA means with respect to the area, where R is the region in the first quadrant bounded by x equals 0, y equals x squared, y equals 8 minus x squared. Well, can I say? 8 minus x squared is an upside-down parabola that goes up to 8. Y equals x squared is an upward-facing parabola. It goes like that. Where do they intersect? Interesting question. They intersect wherever x squared equals 8 minus x squared. So add the x squared to both sides. Divide by 2. Plus minus 2. Of course, we're not interested in the minus part because it says we're bounded by x equals 0. X equals 0 is the y-axis. So it's just that region in there from 0 to 2. All right, so tell me some information about the x's and about the y's. The x's go from 0 to 2, right? That's the only spot where the x's exist. So I might make myself a little list here that the x's go from 0 to 2. How about the y's? It was important for me to graph it so I could figure out which y was on top and which y was in the bottom. So the one on the top is that blue graph. That blue graph is the 8 minus x squared. That's the one that's negative. The one on the bottom is the red one. That's the x squared. So the x squared goes first, right? Lower limit first, upper limit second. And sometimes if you organize this, it makes it a little bit easier to set up. All right, so I'll set it up. I don't know if I'm going to run through all the mechanics, but at the very least, we'll set this up. So it's a double integral. Let's integrate with respect to y first, and then with respect to x. I usually do the messier one first, so let's do the messier one first. X squared and 8 minus x squared, and then the x's we said went from 0 to 2. You're integrating x plus y. So when you first integrate with respect to y, you end up with xy plus y squared over 2, evaluated at y equals 8 minus x squared. Who came up with this problem? And y equals x squared. So you're going to replace the y's in here with 8 minus x squares. Oops. 8 minus x squared. Plus y squared over 2. So 8 minus x squared squared over 2. Okay, that's the upper limit of integration. Now you got the lower limit of integration to do. So replace that first y with an x squared, and you get x times x squared plus x squared squared, so x to the fourth, over 2. All right. This does simplify a little bit. I'm going to save you the time of watching me simplify this whole thing, and I'm going to move over and tell you what I got when I expanded it and then simplified it. So expand and then simplify, and I ended up with negative 2x to the third minus 8x squared plus 8x plus 32. Now you integrate that with respect to x from 0 to 2. And I think at this point you can take it from here. If you want to try it out and check your answer, I came up with 152 over 3. It's not hard, it's just a little bit tedious because you end up with a bunch of fractions. You got to substitute and find common denominators, and then at the end, you'll end up with that answer. So give it a try. I don't think you want to sit here and watch me do all kinds of fraction problems. Let's take a look at this one over here. I said write the integral for the continuous function over this region by first graphing the region, and there's something different about this. This time the x's go from 0 to y times 1 minus y. What's weird about that? This is the equivalent of negative y squared plus y. It's a sideways facing parabola. So this one goes like this. That's the region of my base. Which means if I take vertical slices, I'm going to want to do dx first. Try to avoid slicing from the function onto itself. So the first thing you should do is go this way. Tell me something about x first, and then integrate with respect to y. If I take slices this way with respect to y first, I'm going to end up going from the function to itself. So which way do the x's go? The x's go from 0 to wherever this is over here. This thing here is y times 1 minus y. So my x's go from 0 to y times 1 minus y. The outside ones start at 0, because I could see that they're going to start at 0 here. But what's this number up here? What value do I use up there for my y? Well, what happens if I put a 1 in for y? I get 1 times 1 minus 1, which is 0. Ah, okay. That's where it crosses the axis. And then I just use f of x, y. So there are times when you would want to do the dx first and then the y because of the way that the figure is drawn and how it's sliced. All right, let's take a look at this one over here. This is a double integral with the sine of y squared dy dx. So, what's my issue? My issue is that the sine of y squared doesn't have a simple antiderivative. No, you can't make it negative cosine of y to the third over 3. It doesn't work that way. It's not a lost cause. I could run through trig identities. I could turn it into a Maclaurin series, right? Good old Taylor series, but why? Easier thing is switch the order of operation. Now, when you switch the order of operation, you're going to change your perspective. So you're not taking horizontal slices from x to pi. You're taking vertical slices from 0 to y. So let's take a look at our picture so far. Right now, our region says we're integrating from x to pi. So in other words, I'm drawing y equals x like so, and I'm going from y equals x to y equals pi. And then the x values go from 0 to pi. Instead, I should look at this the other way. So if I want to do the x's first, now where is this going to go on the x's? It's going to go this way here from x equals 0 to x equals y. Right? So this function here is x equals y. So tell me as I go left to right where my x's are going. My x's are going from x equals 0 to x equals y. So the inside limit of integration, I will let go from 0 to y. Integrated how? With respect to x. Now, what are my y's doing? If that's where the x's are going, where are the y's going? That's the easy answer. Here's where your y's are going, from 0 to pi. And that's for the sine of y squared. Oops, let's put the dy there. Good. How is this easier? Well, this is easier because now I don't need a Maclaurin series for it. When I integrate the first round with respect to x, it's just going to pop out an x in front of that sine of y squared, because now the sine of y squared is basically just a constant if I'm integrating with respect to x. So when I do that, I'll end up with what? I'll end up with x times the sine of y squared, replace the x with a y, and then replace the x with a 0. So I'll get a y times the sine of y squared, and then when I replace the x with a 0, I just get a 0. Now I got to do the outside limit of integration from 0 to pi. All right, how do I do this? I need a little u substitution. If you want a little flashback or a little reminder about u substitution here, let's come on the side and integrate from 0 to pi of y times the sine of y squared with respect to y. So here's how I do u substitution. I'm going to let my u be that y squared. If u is y squared, or if u are y squared, then the derivative of u with respect to y is 2y, which means that du is 2y dy. I want half of that. So I want half of du as y dy. So this y and that dy get replaced with a 1/2 du. Okay? The y squared gets replaced with a u. So I have the sine of u. Okay? The other thing I got to worry about is my limits of integration, because now they're not in terms of 0 and pi anymore. Now I want them in terms of u. So if u is y squared, well, the first thing is, let's put a 0 in for y. Zero squared is equal to u, so my lower limit of integration remains a 0. Now put a pi in for y. This time I'll get pi squared is equal to u, so this goes from 0 to pi squared. All right, antiderivative. So the antiderivative of sine is negative cosine, so this gives me 1/2 negative cosine of u evaluated at pi squared and at 0. So negative 1/2 cosine of pi squared minus a negative 1/2 cosine of 0, which is just 1, and there's my answer. I'm not doing anything with the cosine of pi squared. What am I going to do with a cosine of pi squared? All right, let's take a look at a couple of more when we're doing these double integrals. We'll look at one more, and then we'll look at volumes between surfaces, and that will put an end to this section. This one over here, you got to switch the order for the limits of integration to. Why? Well, what am I going to do by integrating first with respect to y? How do I integrate essentially a 1 over y to the 5th plus 1? It's not a u substitution. It's not an integration by parts. There's nothing that jumps out at me as a way to solve it. So I'm going to have to draw out the region and reevaluate my bounds. So when I do this, I may set this up and not get too far into solving it. Let's see. The limits of integration here with respect to y, right? With respect to y, goes from the square root of x to 2. So the square root of x looks like this. Y equals 2 looks like that. So it said that the y's went from the square root of x to 2, so it's that region in there. The x's went from 0 to 4. Is 4 the place where they intersect? Well, what if I put a 4 in for x? Yes, the square root of 4 is equal to 2, so sure enough. And that's a 4, that's a 2. So now, if I want to switch it the other way and I want the x's to go first, where are the x's going? Well, first of all, let's rewrite this in terms of x. So instead of y equals the square root of x, let's write this as y squared is equal to x. So this right-hand function here is x equals y squared. That left-hand function, which is the vertical axis, is x equals 0. So when I go from left to right, where are my x's going from? My x's are going from 0 to y squared. And now the y's are the easier case, right? The y's over here are just going from 0 to 2. So now I've rewritten them in the order that I want to do them. All right, keep the function in mind because it just fell off the screen there. Double integral. We said the inside was the y's, and the inside were the x's, and they're going from 0 to y squared. Right. Double check my memory. Yes, the x's are going from 0 to y squared. So from 0 to y squared is where the x's are going, and then the y's are going from 0 to 2 of x over y to the 5th plus 1. Right. Why is this an advantage? Well, when you integrate that first thing with respect to x, what does it do? That 1 over y to the 5th plus 1 is essentially a constant. So let's keep that 1 over y to the 5th plus 1 on the outside times x. Well, when you take the antiderivative, it becomes x squared over 2, evaluated at x equals y squared and at x equals 0. And a little math magic happens here. When you replace that x with a y squared, you get a y squared squared, which is y to the 4th, and on the bottom, y to the 5th plus 1. Now you can integrate with respect to y from 0 to 2. All right, when you do that, yep, you're going to need another u substitution. This time let u be the denominator, and you notice the numerator falls into place pretty quickly. Should we finish it up? Yes, finish it up. So let's let u be y to the 5th plus 1. Du then will be 5y to the 4th dy. I only want a y to the 4th, so I want a 5th of du. All right, if you do u substitution a little bit differently, that's okay too, as long as we get the same answer. All right, evaluate upper and lower limits of integration. So u evaluated at 2 is going to give me 2 to the 5th, which is 32 plus 1, 33. And u of 0 will actually give me a 1, right? 0 plus 1 is 1. So when I set this up, I'm looking at the integral from 1 to 33 of 1/5 y to the 4th dy is my du over u. All right, now this is easy. 1/5 natural log of u, evaluated at 33 and at 1. And then, at some point, I've got to carry that 2 back in that I completely lost. Oops. Here, let's bring it over here as a 1/2. So now this gives me 1/10 natural log of 33. Natural log of 1 is just 0. And yes, that's my answer. All right, one more thing to look at from this section. And that is, what if I want to find the volume of a region? I point out this picture here just to give you an idea how to find the volume between two surfaces. In two-dimensional calculus, you found the area between two curves by doing what? Like top minus bottom, and that would help you to fill in that area. Well, basically, it's the same thing here. You're going to take the top surface minus the bottom surface and integrate it over some region, right? over the area of the region. That r means you're integrating over that region. So that specific region there is that r. And you would fill in the blanks by setting up an iterated integral. This time your g of x and your h of x are, or g of x and f of x, are not f of x's, they're f of x y's. Not g of x's, g of x y's. All right, let's try one, and then that'll be the end for this section. I've got these two solids. Volume of a solid bounded by a parabolic cylinder, the x squared plus 1, and a plane, z equals y plus 1, and the plane y equals 1. So the plane y equals 1 is on this side here. That's causing it to flatten out, right? So there's basically a wall. That's why this line down the bottom here stops at the wall. That thing over there stops at the wall. So it stops at y equals 1. The x squared plus 1 is that blue region down the bottom. The y plus 1 is the one on the top. So the plane is the higher one. The cylinder is a lower one. And we also need to look at the projection of the solid on the xy plane. So if you look at what you have here, you're looking down on it. You've got a parabola bounded by y equals 1. So where do these rectangles go? The y's go from x squared, which is what that blue curve is on the blue curve, not the line, the blue curve. They go from there up to 1. So if I draw things like this, those are what? Those are the y values. The y values have a minimum of x squared, right? They touch the parabola. They don't go all the way down to the axis. They only go down to the parabola. So they start at x squared, and they end at 1. The x's now are easy. If we're going to integrate with respect to y first, which we probably should, then the x's just go from -1 to +1. How do I know that? Here and here, right? When y is 1, x is 1, 1 squared is 1, -1 squared is also 1. So the x's go from -1 to 1. And now we need to set up our integrand. So the top one is y plus 1. The bottom is x squared plus 1. So the top one we said was y plus 1. The bottom we said was x squared plus 1. We're going to do a double integral with respect to y first. And lower limit is x squared, upper limit is 1. The x's go from -1 to +1. All right, then from here, the rest isn't too bad. I'll set it up, and then I'll leave you to do the numerical calculations, and I'll tell you what I got at the end. Did I lose, or did I just not write? There we go. All right, combine things. I'm going to end up with a y plus 1 minus x squared minus 1. And now you see the advantage of doing a little quick simplification first, in that this inside piece simply becomes the integral from x squared to 1 of y minus x squared with respect to y. So when I integrate with respect to y, what happens when you already have a y? Add 1, divide by the new power, y squared over 2, minus x squared y, evaluated at 1 and at x squared. That 1 and that x squared are y values. So I'll end up with a half minus x squared. That's my first piece. Now, minus a lower limit of integration. So replace that y with an x squared. You'll get x squared squared. And now replace that y with an x squared. You get x squared times x squared, which is x to the 4th. All right, combine terms a little bit, simplify, and integrate with respect to x. All right, so if I simplify this, I get a 1/2 minus x squared minus a half x to the 4th minus gives me a plus 1x to the 4th. So I got the integral from -1 to 1 of a half x to the 4th, right? Because that's what happens when I take 1 minus a half, minus x squared plus a half, integrate it with respect to x. All right, so it gives me x to the 5th over 10, right? Because there's a 2 down the bottom. Now divide by the new power. 2 times 5 is 10. Minus x to the 3rd over 3 plus 1/2 x. Evaluate a 1 and negative 1. I'm going to spare you, because we're past the 30-minute mark at this point, I'm going to spare you me substituting each of those numbers in individually. You can believe me or not believe me, but I get 8/15 as my answer. If you want a little practice with a fraction, it might not be a bad idea for you to throw those in and see if you get those same numbers. So now we've done 2 different types of regions. The next section we'll start looking at polar coordinates.